Well, hi there. I'd like to say a few words about fault geometry modeling using some specific examples. In the 1950s, Hafner proposed a very elegant method that he published in the GSA. It is mentioned in many structural geology textbooks and in several references. Now, keep in mind that Hafner did this work before we had gained much knowledge from experimental rock deformation. I have been able to successfully apply an updated version of this old technique in some of my study areas. By the way, I'm Robert Font, a certified professional geologist and an active member of the AIPG. A basic premise is that fault patterns can be predicted from the fracture patterns that develop from a common stress field. Now, our knowledge of fracture geometries comes from field observations, from experimental rock deformation, and from theoretical geomechanics. Point in case, the Coulomb-Moore fracture criterion. The bottom line is that we know that shear fractures occur at angles of about 30 degrees to sigma 1 and 60 degrees to sigma 3. Sigma 1 being the major principal stress and sigma 3 being the minor principal stress. Therefore, we can quantitatively model fault geometries using methods such as the Hafner solutions. To solve the problem, we use the biharmonic equation, which is the equation that is shown above. The biharmonic equation is the compatibility equation in terms of the area stress function. The area stress function automatically satisfies stress. Remember that the compatibility equation ensures that the strain is compatible with and derivable from the displacements. So when the biharmonic equation is satisfied, we have automatically satisfied stress, strain, and the theory of elasticity. We can find solutions to the biharmonic equation by setting specific geologically realistic boundary conditions, and that is the hardest part by far. Also selecting a mathematically convenient form of the area stress function. Commonly, we can either select a third degree or fourth degree polynomial function in two variables where the coefficients can be arbitrarily assigned. The equation that you see above is a fourth degree polynomial function. In solving the biharmonic equation, we can generate sigma 1 and sigma 3 stress trajectories, and from those we can predict the related fault patterns. The main challenge, for sure, is to ensure that we can create a geologically realistic model and not purely a mechanical one. And I can tell you that a certain degree of trial and error is typically necessary to achieve our desired solution. Let me illustrate the point with some specific examples. From actual strength tests conducted in the lab, I modeled an earth block 8 kilometers long by 3 kilometers in thickness. I also established an approximate linear relationship between the ultimate strength and depth for a specific shale, a limestone, a sandstone, and a dolomite. I did this based on normal pressure temperature gradients and a strain rate that is consistent with faulting. As I mentioned earlier, the real challenge is to establish boundary conditions that are geologically realistic. In this model, I assumed a tectonic horizontal stress that consists of a push from the west, in other words, from left to right. So the horizontal tectonic stress decreases from left to right, varies linearly, and has a constant gradient in the horizontal direction. I also assume that the tectonic vertical stress is pretty much negligible, and the tectonic shear stress is constant along horizontal planes and increases vertically at a constant rate. All of this is superimposed on the standard state or the hydrostatic condition. Once we have our boundary conditions, we can write our equations for the horizontal tectonic stress, the vertical tectonic stress, the tectonic shear stress, and two very important equations would be the equations of the maximum shear stress at failure and the equation for the angle theta, theta being the angle between the minor principal stress and the fault plane. A major assumption is that when tau max, the maximum shear stress, is greater than the ultimate strength of the rock will rupture and the faulting will take place. For each rock type, we develop a table like the one shown here, so that for each x and y value, there are specific values of tau max and theta. When tau max is greater than the ultimate strength, faulting will occur. If tau max is less than the ultimate strength, the rock remains intact. So then what is our fault geometry based on this model? Well, for a single lithology, the shale in this particular case, our boundary conditions yield the illustrated fault geometry. As you can see, it's a conjugate set of reverse faults affecting the western part of the block. These faults make an angle of 30 degrees to sigma 1 or 60 degrees to sigma 3. But be aware that lithologic complexities can affect zones of stability versus fracturing, as well as local fracture geometry. In a multi-lithologic model, note that under the same identical tectonic stress system, the zones of stability versus faulting are changed depending on the specific sequence of the different rock types involved. And here's the punchline. Realize that adjusting boundary conditions will yield varying results. Our task is to find out what best describes the actual deformation that we see in the field or from geophysical data. Well, that's it. Hope you have learned something. Take care. See you later.